Welcome back to Make Talks. In our last videos, we explore phase diagrams and how they control steel macrostructures. We talk about several videos. The first one, mastering phase diagrams, lever rule, phase fractions, and mechanical strength. The second one was eutectic alloys in actions, hypo, hyper, and weight fractions calculation explained. And the third one was about eutectic alloys, it was about the eutectoid, pretectic macrostructure, and ferrite, perlite, austenite, and the last one was hypo versus hyper eutectoid steels. And we talk about the details of how austenite convert to perlite and proeutectoid phases that may be proeutectoid alpha or ferrite or proeutectoid cementite or Fe3C. Okay, today we want to talk about the TTT diagram. And what is TTT diagram? It is the time temperature transformation diagram, which shows not just what phase forms, but how fast they form and in what sequence we have them. This is crucial for us as mechanical engineers. Why? Because the cooling rate and holding time can affect on final macrostructures of the material, and therefore the material strength, hardness, ductility, and toughness, because all of them are related to final macrostructures. Okay, in this video, we do three main things. First, we explain TTT diagram, why they are important for us, and how carbon content, as you know, C%, that is different between 0.022 or 0% to 6.7%, affect phase transformation. Second, we discuss what information TTT diagrams provide that regular phases diagrams cannot. That means about anything that we talk about phase diagram, you didn't see the effect of the time and cooling rate on that. So, like the kinetics of transformations and the formations of intermediate structures such as bainite or martensite. And third, and the most importantly, we work through practice problems for 0.45% carbon weight percent of steel, and we will calculate the fractions of different final macrostructures, means how much we have martensite, bainite, perlite, depends to cooling rate and time that we hold at that temperature. Okay, so, let's start. What is TTT diagram? TTT diagrams are time temperature transformation diagram. Definitions means this diagram shows how austenite transform into another macrostructure, such as bainite, perlite, or martensite, as a function of time and temperature during the isothermal holds. It's very important to know that only austenite convert to perlite or bainite or martensite, not other structures. Means if we have, you see in examples, if some parts of the austenite converted to perlite and then again we cool fast to martensite temperature, that part that converted previously to perlite not convert to martensite. So only austenite conversion to other macrostructures. Okay. The next one, what is the importance of TTT diagram for us as a mechanical engineer? They link the thermal history of steel to the microstructure form, helping engineers, special us as mechanical engineers, to design effectively heat treatments. And we enable to predict and control final properties such as hardness, strength, ductility, and brittleness by selecting appropriate holding time and temperatures, or how much temperature should heat treatment or cooling at that temperature. Another things that I want to talk about that is about the properties that you can see here. I try to cover all aspects that shows, for example, we have austenite, sorry. We have austenite and we different cooling rate. For example, if we have slow cooling, we reach to perlite. Do you see here P means perlite? And if moderate, we reach to bainite. And if so rapid quenching, we reach to martensite. These three horizontal line that you see here, 0%, 50%, 90%, means a start of the martensite, 50% of austenite convert to martensite, and 90%. And if we reach to, for example, from A78, that is above eutectoid temperature, we quench to room temperatures, means 100% in one step from austenite convert to martensite. Okay, if we have martensite and reheat that, we have tempered martensite. For example, if we reheat up to 350 or something for 1 hour, we have the tempered martensite. Here you see the property. Here, a strength increase means the minimum strength is related to a spheroidite. A spheroidite means hitting at 700 for a long time, not 1 hour, such as tempered martensite. After that, coarse perlite, we have fine perlite, bainite, tempered martensite, and martensite. So the maximum strength is related martensite. And ductility is completely vice versa, means the maximum ductility is related to spheroidite and the minimum is for martensite. Okay. And another thing that is important is the carbon content of that. Means that for different carbon content, especially this TTT diagram is related to eutectoid, hypo, and hypereutectoid. If you remember for STL, if the carbon between 0.022 and 0.76, we say hypoeutectoid. And if C between 0.76 and 2.14, we say hypereutectoid. So for different carbon weight percent, we have different TTT diagram. So you should pay attention. If the problem says that at 0.76 or as the weight percent of eutectoid, only you should focus on TTT diagram for eutectoid weight percent. Or if 0.45, as same as practice problems that we today solve, that means we have different TTT diagram. Okay. Here, start with the practice problem that have several parts, but we read that and carefully pay attention. We have the steel containing 0.45 weight percent carbon. So C naught is 0.45%. So this TTT diagram is only for this carbon weight percent. So if you are talking about eutectoid, means C naught is 0.76, you should use other TT diagram, okay? Carbon is fully austenite at 845 degree. Do you see A here? Means all area that I show here by dash, they are austenite. So this red one is austenite, okay? And we have complete and uniform austenite structures. Using the isothermal transformation diagram or TTT diagram for 0.45% carbon, determine the final microstructure that forms in each of the following heat treatment. Identify the macroconstituents percent and estimate their approximate percentage. Okay. Let me clean that and start by part A. Okay, it says that rapidly cool to 320. Okay, these temperatures is 320 and this temperature, as the problem said, it was 845. Okay, rapidly cool up to these temperatures, hold 400 seconds. Look at here. This time is approximately 0.4 or something. So our time a little should be more than 100. Up to here, we hold at this temperature for this, and then quenching to room temperature means this temperature should be, for example, 27 something centigrade. Okay. I write all information that we have. At 1, we have 100% austenite. Okay. At 2, some part of that, for example, at 320, some part of that more than 50%. For example, 70% convert to martensite, yeah. Um, convert to martensite, and then by cooling again up to room temperature, we reach to 100% martensite. Okay, so here I should change that, not 35%. Why? Because it's 0%, the red one. The blue one is 50%, is 100%. If you consider 100 exactly here, it's between 50 and 70. So I approximately say 70%. So while rapidly cooling to 320, 70% transform to martensite during 100 seconds in isothermal treatment at 320. No additional transformation occurs. During the final cooling, means from 2 up to 3, the residual or the remain of austenite convert that to martensite, so 100% martensite. But it says that after quenching to room temperature, then reheat to 350, 15 and hold for 1 hour. So we have another stage that you cannot see in TT diagram. Why? Because heat treatment it has not shown here. It is for cooling rate. If we increase temperature to 315, for example, for 1 hour or 2 hours, we have tempered martensite. How much percent? At 3, we have 100% martensite. So 100% martensite now convert to tempered martensite. So as you see inside the parentheses, the macrostructures consist of 100% tempered martensite. Okay, part B. Rapidly cool to 700. Hold for 20 seconds. So it is 1. It is 2, and then quenching to room temperatures. Okay, I changed the color. At 1, we have 100% austenite. At 2, look at here. What is A plus F? A plus F only we have if C is less than 0.76. If you remember, we say it is hypoeutectoid. In hypoeutectoid, always we have proeutectoid alpha in phase diagram plus perlite. Yeah. But here you see other phases except perlite, such as benite, martensite, or something that you couldn't see that in phase diagram. But A plus F means austenite plus ferrite. Which ferrite? Proeutectoid ferrite. Okay, at 2, look at here, we have 2 red curve. This first red curve means a starting of proeutectoid ferrite. The second red that here you see, it is 0% of austenite convert to, for example, other phases means perlite here, and below that means benite. Here is 0%, above 0%. The blue one, blue dash line is 50%, and the green one, I think, the color is green, I think, is 100%. Yeah, but this red one that you see here is a starting that means between these two parts, only between these two parts, we have austenite plus proeutectoid ferrite. It's very important. So as you see at 2, we are completely between these two red lines, and we have not reached to 0%. So what's the meaning of that? Means we have proeutectoid ferrite at 2 plus austenite. While cooling again to a 3 or room temperature, austenite convert that to martensite. So at 2 is here. At 2, we have austenite and proeutectoid alpha or ferrite. But austenite not convert to perlite. Why? Because not reach to 0%. Austenite uh, didn't have enough time for converting to perlite. If we hold that temperature up to, for example, this time is approximately between 100 and 1000, it is logarithmic the time. Up to this, we can say, okay, austenite had enough time for converting to perlite. So here at 2, we have austenite and proeutectoid ferrite. Any part of austenite not convert to perlite. And at 3, 100% of austenite, because we reach to room temperature, and it is 90%, this temperature is below, that means 100% of austenite convert to martensite plus proeutectoid alpha. Again, if we have other phases except austenite, keep its original macrostructures and not convert to other phases, okay? So if we have perlite, not convert to martensite. If we have proeutectoid ferrite, not convert to martensite. The only things that, because of quenching, convert to benite or martensite or something is austenite. Okay. So at final macrostructure is martensite and perlite alpha. What is weight percent of martensite? Exactly the weight percent of perlite that you calculated with lever rule in phase diagram. And proeutectoid alpha, again, exactly is the weight percent that you calculated by using the lever rule in phase diagram. Here, C naught is 0.45. Eutectoid weight percent is 0.76, if you remember. The maximum of alpha or ferrite is 0.022. Okay, use the lever rule. It is the perlite, it is the ferrite or alpha. Which side from far from alpha? This side is so W of ferrite, you can say that 0.76 minus 0.45 per 0.76 minus 0.022, that is 0.474, and W of perlite is 0.44 minus 0.022 per 0.76 minus 0.022. And summations of both of them should be 1. Here, find the perlite or martensite. I told that the weight fraction for both of them say, because the perlite that you saw is phase diagram, now is martensite. Okay? Yeah. So it is 58%, and 1 minus this is 42%. It is ferrite or weight fractions of ferrite. Okay. Rapidly cool to 400. Again, here C is 0.45, and no need to say that we only use TT diagram for this weight. Percent of the carbon. And if you are using for eutectoid, you don't see any pro-eutectoid phase such as A plus F that you see here, or for more than 0.76, you see austenite plus cementite in this area. Okay. Rapidly cool to 400. Keep that, so it is 1. It is for 10 seconds, it is 2, and then quenching to room temperature. At 1, we are in austenite area. So at 100% austenite. At 2, look at here, a little more than blue dash line between 50% and 100%. Approximately, I say 55% or maybe 50%, but not much different. So 55% is bainite, because here in this region, here we have perlite, and here up to 0% we have bainite. But pay attention for perlite. For example, more than 650, if we cool more than 650, we have coarse perlite, and less than that, we have fine perlite. But here, no matter, because we are talking 400, so 55% of austenite convert to bainite, and another 45% doesn't have enough time, and again is austenite. But at 3, 55% of bainite not change, because I told that this diagram, TTT diagram, is only talking about the transformations of austenite to other phase. But austenite, 100% of 45%, that again is 45%, convert to martensite. Okay. Part D, rapidly cool to 700. So it is 700. Hold at this temperature 1000 seconds is 2. And then quenching to the room temperature. So at 1 is 100% is austenite. Yeah. At 2, after 1000 seconds, we have proeutectoid ferrite plus coarse perlite, but 100% coarse perlite. Look at here. We extend, and it is the green line, or 100%. We beyond the 100%. So 100% here we have A plus F means we have proeutectoid ferrite plus 100% of perlite. But which perlite? I told that less than 650, we say fine, approximately. More than that, it is coarse. So here we have coarse perlite. Then quenching. When quench, only austenite converts to martensite, yeah? Or if the, for example, is cooling above 320 or something, convert to bainite or something. But only austenite. Here, at 2, we had proeutectoid ferrite, so be this again, not convert. We had 100% coarse perlite. Okay, no longer change. Why? Because only austenite change. Okay, so again here we have proeutectoid ferrite and coarse perlite. Again, we use lever rule that we had in phase diagram for weight percent of the alpha and coarse perlite. Again, we are 0.45, 0.76 that it is eutectoid. We are here, and here is the ferrite, or we say here is perlite, or maybe in the TT diagram convert to martensite, bainite, or some things. All of them is related that proeutectoid ferrite is here. Proeutectoid, and it is a lever rule. Okay, we say which side far from that. For perlite, which side far from that? This side 0.45 minus 0.022 per total length, that's 0.76 minus 0.022, 58%. We have the coarse perlite, and 1 minus that because summation 100, we have the proeutectoid ferrite. Okay, rapidly cool to 610. 610 is here. It is 1. 610 is here. How much we are here for 10 seconds? 10 seconds is here. You see that is more than 100% because here is 100% convert to perlite, but it is less than 650. We expect that fine perlite. But as we reach this region, definitely we have proeutectoid ferrite too. When we get rid of the proeutectoid ferrite, if, for example, it's cooling up less than this temperature, yeah, means above this temperature, that is 5.8 something, in this region, we have proeutectoid ferrite. But if we cool less than that, 100% convert to bainite, or we quenching martensite or some things, and we don't have proeutectoid ferrite. But if above these temperatures, any temperatures above 580 or something, definitely we have proeutectoid ferrite. So we have proeutectoid ferrite at 100% austenite. At 2, we have proeutectoid alpha or ferrite, and 100% of austenite convert that to perlite. But which perlite? Definitely fine perlite, because it's so close to this dash line. What is this dash line? Border between perlite and bainite. Okay, again, we use lever rule. I don't think no more need to talk about the lever rule that we had in phase diagram. Fine perlite weight percent, exactly use the equation that we used for the perlite in phase diagram, and 100 minus that is the weight percent of proeutectoid phase, that here we have proeutectoid ferrite. That's all for today's deep dive into TTT diagrams, where we explore how austenite transform into perlite, bainite, martensite, tempered martensite, spheroidite, and I talk about the property of all of them, talk about proeutectoid phases. I told that if C less than 0.76, maybe we have proeutectoid ferrite, and if C more than 0.76, maybe in cooling we have proeutectoid cementite, and I told that the temperature is very important. So you have seen how cooling rate and isothermal holding times control the fractions of each phase, and how these transformations directly affect material properties such as strength, hardness, ductility, and toughness and brittleness. If this video help you master the connecting between TTT diagrams and phase diagram and real-world materials behavior, give it a like or share your thoughts in the comments. And don't forget to subscribe to McDocs 2025 and turn on notifications so you will not miss new videos about the heat treatments, material characteristics, and engineering problems. Thanks again for watching this video. Keep exploring the science behind the strong materials, and see you in next video. Thank you so much.